And we have a keynote talk titled Video Quality, a Nexus of Video Engineering and Visual Neuroscience. And the speaker is Al Bovik. I suppose he doesn't need much introduction. Most of you are familiar with him. So Alan Bovik is a Corcoran Family Regent Endowed Chair Professor at the University of Texas at Austin. His research interest lands at the nexus of visual neuroscience and digital pictures and videos. His recent interests include immersive, virtual, and augmented visual experience and how they can be perceptually optimized. Very interesting topics. An elected member of the US National Academy of Engineering, his many honors include the IEEE Edison Medal, a Primetime Emmy Award, and a Technology and Engineering Emmy Award. You are very welcome, Al. You can start. Okay.
1, 2, 3, testing. Oh, good. Okay, well, thanks for having me in your excellent conference in this beautiful city amongst these incredible mountains. I'm going to talk about video quality, and in particular, some of the visual neuroscience around it. People are using video quality models quite extensively these days, and I want to help make sure that people understand that there really is a perceptual, a visual neuroscience underpinning these models. That's why they work. They're not heuristic, they're not ad hoc, and they really have foundational science. Isn't this a great picture? I mean, I wouldn't change it for anything, even though it's got a lot of different distortions in it. It was actually taken by a student in my image processing class. The homework was, gather a bunch of pictures. The next homework was, write an algorithm to predict picture quality, okay? If you've been to Austin, you might know where this picture was taken. Anybody been to Austin and can guess this? 6th Street, if you've been there, okay? Anyway, when I show this in my class, I show them this question: how many distortions can you find? There's a lot, of course. There's all kinds of, well, I spent about 30 seconds writing some down, you know, various kinds of blur, over and under exposure, jitter, low light noise. You can find a lot of these things. And of course, these things combine to create more distortions. You put them together, there's something else. And I can tell you, having worked in this field for going on 3 decades, I don't know of a real-world distortion that you can successfully model. I think it's really impossible. And I'm talking about common things like blur and compression. You can't really model it in any reliable way. Okay, so how do we predict quality? Oh, this is a video. You might consider, is this a high-quality video? Well, you know, it depends on your context. This is the highest quality video ever taken of this particular subject, known as Bigfoot. But nevertheless, I think we'd identify an enormous number of distortions, some of which will be relevant to what I'm talking about today. Okay, so we know that video quality is a pervasive problem. It has been ever since the photograph was first invented. So ever since video was first invented. Today it's even more important because most internet traffic is pictures and videos. I typically hear the figure 80%. That may be going up. Maybe this crowd knows that it's heading towards 90. In any case, it is the most important big data, and it's everywhere. Now today, I'm going to talk about high quality content, which is typically compressed, scaled, streamed, that sort of thing. But I want to recognize that there's another category called user-generated content. These are sort of bifurcated because typically you have a reference signal available because it's high quality. And with user-generated content, you do not. So I think everybody here knows about reference and no reference. I'm going to be talking about reference quality, partly because I want to explain some of these perceptual principles for those that don't have that background a little bit, and also got some new results in that space. Okay? So again, many, many different kinds of distortions. They can include all kinds of degradations, creating new distortions. You can't model any of this stuff. So how can you possibly approach it? Well, I remember talking to my advisor, Tom Wong, back in the 1980s. We wondered I was working on median filtering, and how do you assess the result? How is it better? And we just put a picture in the grainy transactions. We didn't have a way. And Tom and I both concluded, really, there is no way known to do it other than the very fallible mean squared error. Early 2000s situation is the same, and I had conversations with my students Joe Wong and Hamid Sheikh about the same thing. And this is when we embarked on the problem, which at that point in time was still regarded as insoluble. You could read Pratt's book and say, this problem seems insoluble, something like that. Okay, it's very important because it affects user experience, bandwidth usage, and so on. So if we can't model it in the picture, in the video, what do? Turns out the way to model it is in the responses of the neurons in the brain, in your brain. Then we succeed, as we'll see. So I'll be talking about this scenario here. Next time I could talk about this. Lots to talk about there too. Okay, so in this space, we're all working on video communications from one place to another. But if we want to be most accurate and solve this problem, we have to realize, well, the transmitter isn't an antenna. It's the world of photons being reflected off surfaces and being captured. The receiver, again, isn't an antenna or a television set. It's your visual, it's your eyes, it's your visual brain. As with any communication system, the better job of communicating you can do if you can model the transmitter and if you can model the receiver to create better communications. In between is the channel, where there's a lot of stuff going, all sorts of processing, compression, transmission, stuff that they do at the streaming and the social media servers, and so on. Distortion is everywhere. That's what these blinking red arrows mean, places where distortion can and does happen. So many places, so many kinds of distortion. How do we account for it? How do we handle it? That's the topic of video quality. Okay, so again, you guys know these distortions. These are all familiar things to you, and I think any one of you could list many more distortions that are mostly spatial. You see it in the frame even if you freeze it, and some that are mostly temporal, that are mostly revealed when you run a video, and you see it passing over time. Okay, and once again, people have studied trying to model these. Let's make a model of a block, from compression, that sort of thing. And they don't really work in the long run. They don't really create accurate video quality prediction models. We have to instead look inside the brain. Okay? So it's hard. There's more to it than just looking inside the brain. Videos help us out, actually. It's a really hard problem, but because videos are special in certain ways, statistical ways, the problem becomes solvable. At least we're making progress on solving it. And because distortion changes their specialness. And I'll talk about some of the ways in which videos are special. Okay? Now, since videos are special in pictures, things captured photographically, our eyeballs, our cameras, our brain expects that specialness. If the specialness is broken by distortion, the brain is instantly aware of it. When you look at a picture and it's blurry, you don't think, well, is that blurry? It's blurry. Pre-attentive, precognitive. The brain understands the specialness, which we can describe in a statistical way, has been violated. So here's the first special property of videos I'll talk about. There's actually many, but I picked these three because they affect the models I'm going to be talking about shortly. First of all is the reciprocal model of pictorial information. E here means expected value. It's basically a way of saying that we expect that the power spectrum, this is a Fourier transform, magnitude, you could square it if you want and get 2 here. The power spectrum of pictures is universally approximately reciprocal. You hear it often described as 1 over f. This is an old result, okay? Typically, the exponent here, it's usually often said, well, it's about 1. In truth, experimentally, and extensive studies have been done, it's usually around 1.2 on pictures and videos that have been at least digitized. This is true whether we're measuring spatially the spectrum or in the time dimension. They're also 1 over f along the time dimension, okay? Now, mathematically, first of all, we know something about the spectrum on average. Doesn't mean every video is perfectly 1 over f, but you've looked at Fourier transforms, DCTs, DFTs, and that's what you see. A lot of low frequency energy, it falls off like this. Well, if this property is true, it also means that videos have the self-similarity property. This goes back to Benoit Mandelbrot, who observed this self-similarity. This is a unique signal. If it's self-similar, it obeys this property, and vice versa. Videos and pictures are self-similar. This means that they have a multi-scale description. Multi-scale signals, just like in the old days, electrical engineers, radio engineers, what do? We analyze the bands. We do a multi-band analysis. And I'll be going there next after motivating it. First, just want to show you one. If I can find my arrow. This is a video where there's a lot happening. Somebody's shooting down. Can you see it? Good. Shooting down the chute. And this is a log scale, of course, so it's should be approximately linear. This model is only approximately true for videos. Universal as it is, it's only approximately true. You don't get actually usually a perfectly straight line, but it's approximately true. On the left, spatial power spectrum. In other words, a phrase. On the right, temporal power spectrum along the time dimension. Pick any video that's of good quality, and you'll find this kind of behavior. Okay, second cool property. We all know about Fourier transforms, DCTs, DFTs, and so on. We can write it. We think of it as expressing a video or a piece of a video, and I'm going to focus on pieces. Think of a block or a patch in a frame for now. You can express it in an expansion, a weighted sum of basis functions. DCT, it's cosines, etc. Now, we can find a basis representation of a video patch by minimizing the error between the representation over the weights and the video itself. Now, if you insert an orthogonality constraint, this is called PCA. The DCT is very close to the PCA, which is optimal amongst decorrelating transforms of this type. But back in the 1990s, a couple of vision scientists, and at the same time, a statistician named Robert Tibshirani at Stanford asked the question, what if we get rid of that? We don't insist upon any orthogonality or energy constraints or any of those usual things. We instead insert a sparsity constraint. Okay, the idea is we add a function that, when this is minimized, causes the outcome to roll down these hills and get caught in these little sharp crevasses, which lead to a lot of zero coefficients. This was the beginning of sparsity theory, which roared along and still is very important today, even affects the design of deep networks. Okay? What did they find when they did this? They found basis functions that look like this. Bandpass filters. Bandpass filters. These filters actually look a lot like what are called Gabor filters. Gabor filters are the model of the simple cells in primary visual cortex. In vision science, we model the passage of the visual signal to the back of the brain, where a massive wavelet-like decomposition occurs, using concentrated sparsity filters like this. If we train a deep network on ImageNet or something, by the way, and look at the early layers, those early layers' weighting functions look like this as well. Okay, so in solving visual problems, both deep nets and our evolving brain find sparse representations by decomposing into bandpass signals. That's special property number 2. Bandpass signals are found throughout our visual system. At the retina, right here, if you've studied the retina at all or taken a computer vision class, the retina is modeled using linear systems theory as a simple bandpass filter called a difference of Gaussians filter, a center surround filter. Okay? In the lateral geniculate nucleus, temporal processing occurs along the time dimension. These have different models. They're causal models typically. It's modeled as a gamma filter, modulated by a sinusoid. This is a foundation of temporal vision science. Okay? Both of these are bandpass filters. Visual cortex, as I mentioned, you get bandpass filters that are directional. They look like Gabor functions or derivatives of Gaussians, that sort of thing. Now, what is the vision system? Why is the vision system doing this? Well, one is because it's matching this special property of visual signals. It's creating sparse representations, okay? Back in the 1950s and 60s, there was a visual psychologist. His name was Horace Barlow. He developed what was called the efficient coding hypothesis. The hypothesis was, what is the vision system doing at first? What are all the neurons doing, those billions of neurons? Well, he realized there was so much visual information entering the brain, incident on the retina, it was all devoted to, well, video compression. Compressing the video, finding efficient representations, and the way the brain does it is with bandpass processing. Bandpass processing. Okay, so those are a couple of special laws. The third one, the most amazing one, okay? This one will use a little math. Suppose that I have my video F, okay, and I filter it with a bandpass filter H, okay? Well, bandpass videos can be reliably modeled by what are called Gaussian scale mixtures. It's a random field representation. In this random, it's actually very simple. It's a variance field which contains information about details, texture, structure in the video, that sort of thing, and basically Gaussian noise. Very interesting. The implication is that, well, this is the information used for things like recognizing objects in people's faces, your mother and all that sort of thing. What is the noise part for? What is the noise part for? Well, I believe that the noise part is implicated in the brain's perception of visual quality. And we can support that going forward, okay? So bandpass processing of video creates a model that is very reliably modeled as Gaussian scaled mixture. Okay? If you took 1 billion videos all over the world with 1 billion different cameras, they will all obey this model. It also suggests that if we estimate this local variance field, divide it out, or condition on it, all we have left is this sort of Gaussian noise. Okay? Why is it there? Okay. Under the Gaussian scale mixture model, we can actually find the density function. And we can estimate, using maximum likelihood, the variance field. This guy right here. We can actually estimate it, meaning we can then divide it out or condition upon it. If we do that, all that remains is this Gaussian noise. So every picture or video obeys this property if it's of high quality. The amazing property of visual signals are that they have an underlying Gaussianity if they're of high quality. And it has nothing to do with the central limit theorem. Nobody's been able to explain it yet, and great minds have. Nobel laureates, Fields medalists like David Mumford studied this, could explain why it happens. He studied this area for quite some time. It's one of the foundations of vision science today. Underlying Gaussianity of visual signals. Okay. This shows a picture, a couple of frames. They've been bandpass and divisibly normalized. Estimate that variance and divide by it. This shows a histogram of the result. It doesn't look Gaussian because it's a log scale. Log scale, okay? You can see the Gaussian on a log scale under it. It's almost a perfect overlap. Again, this is a very reliable model. Okay, let's go back to what happens inside the neurophysiological system. the neurosensory system. Visual neurons and other neurons in our hearing and our sense of touch, they all undergo a process of normalization of their outputs. A well-accepted model is that the output of a neuron, which we can model as just a bandpass filter, is divided by the energies of neighboring neurons that are added up. Okay, so here's sum up the energies, divide. We can do this using algorithms, but it's also what's done in the brain. Okay? So these can be ganglion neurons or they can be cortical neurons. The same kind of normalization occurs. Why does the neural system do this? Well, because neural signals can be arbitrary magnitude otherwise. It's a way of constraining them to a smaller space, of course. They can be handled much easier, they're more compact, more predictable in that way. Okay? But it also explains certain visual phenomena, including the famous contrast masking effect. So in this picture of a little girl, you can see there's a lot of compression artifacts on the smooth parts of her face and arms. In the background, which is very busy, think about dividing by the local energy of neighboring neurons, high energy, the distortions are almost invisible. You have to get up close, and then you can find them. If I subtract the original from this, you just see these uniform JPEG artifacts. Of course, this perceptual phenomena is really important in video quality prediction. You have to account for it. Because here you'd say, oh, that's pretty good quality, and here this is terrible, okay? Setting aside the projector, of course. Okay. So how to use this kind of statistical model, universal model of pictures and videos at the neural level to predict quality? Well, the basic idea is, suppose I have a picture and maybe a distorted version of them, process them both using this simple perceptual model, bandpass processing, maybe a whole band of bandpass filters, divisively normalize them, okay? Look for Gaussianity features, okay, which we can define as forming some space of near Gaussianity in some high-dimensional space of measuring features to predict, to measure Gaussianity. If a video has features that fall close to ideal Gaussian, it's of high quality. It turns out that it's true, and this is the basis of famous algorithms and explains other ones. If it's outside, it's going to be of low quality. Okay? Notice I have two little red arrows. In one case, we could measure these derived features to the ideal Gaussian. Notice I'm not using a reference video then. That's a no-reference way of measuring quality, and that's a different talk, as I said at the outset. No reference quality. We just measure distance from Gaussianity. But we can also measure the distance to the ideal references features. That's the reference model we're going to talk about. Okay? So let's go right ahead and do it. Okay? The scenario, again, is a reference scenario. I've got a high-quality videos that are distorted by these guys, compressed, scaled, test video. We want to make comparisons between these before we stream, either on a per-shot basis, in real time, whatever. So here's the simple scenario. A reference and a test video frame. This is a spatial measurement of spatial information loss. First, we conduct our perceptual processing. We bandpass process the signal, okay? Multi-scale cortical model. We use steerable pyramids, a common model for primary visual cortex. We measure the local variance field, and we compute the entropies conditioned on that local variance field. I'll show you the math in a minute, okay? We do some scaling and pooling, and then we just compare these. Well, look at subtraction, okay? And then some pooling, I'll get into that later, to obtain quality-aware spatial features. Then we can do the same thing. Instead of on frames, we can do it on frame differences. Notice we're only using 2 frames here. Later I'll talk about using more. So on 2 frames, exact same flow diagram, pretty much. Frame difference of the reference, frame difference of test. Perceptual processing, statistical modeling, compute entropies. Entropy is measuring information. Distortion causes a loss of information or added information like blocks or noise. A difference in entropy. Very natural approach. Information. Same kind of pooling and so on. Quality-aware temporal features. Okay? So once again, I'm going to lay it all out very quickly. Gaussian scale mixture model. Our video, which is bandpass, modeled as the product of a variance field and basically noise. Oh, I added one other term. I'm adding a neural noise model, a noise model. The noise model measures uncertainties in the visual system, imperfect lens, the actual neural noise that occurs in your neurosensory system, which the vision system sees through. Including a neural noise model makes all of this much more accurate in the end. We apply this model to this is a cross product, original frames, original frame differences, distorted frames, and distorted frame differences, so we can compute this flow, okay? We use the same maximum likelihood estimate for all four of these, original, distorted frames, frame differences, distorted frame differences, for the variance field. This shows the closed form expression for the conditional entropies after all this processing. We just calculate it. We know how to, under this model, okay? Then I mentioned that there was some scaling, okay? In this perceptual scaling, we basically scale by the logarithm of the local energy, the variance field, in space and in time. The idea there is also perceptually motivated. Places that are busy with texture and all that sort of thing, or blocking, are a little bit more important, okay? It also lends a little bit numerical stability. All right. So, a number of models, and there's other ones too, but these are sort of the main ones. The original model that used this kind of thinking, the Gaussian scale mixture model for video quality, was called visual information fidelity. It was used by a very large company to stream their videos even back before 2010. Okay? Space-time reduced entropic differencing, ST-RED, that's one of our models as well. And then the famous visual multi-method, I always get confused saying it, VMAF, which is used throughout the video space today, used to control such a high percentage of video traffic. These models are all very closely related. They're all based on the neural models, the neural processing models, the statistical models I've just described. And now they're used to control the quality of most of the visual internet. The only other model that competes is an old model, SIM or multi-scale SIM. That model, by the way, can be explained using the Gaussian scale mixture that I just described. That's why it's successful as well. Okay? Today, the internet is a visual internet. Not only that, it's an internet in which the principles of visual neuroscience have been injected throughout. It's a visual neuroscience internet today. And the streaming companies and social media companies that are using this and studying it are neuroscience companies today, not just data streamers. I'll just show you a couple of examples. ST-RED map. This one's easy, so there's only one subject. Before and after. It's distorted by compression. You can see the response of ST-RED. Brighter means lower quality in this case. Here's another one. Maybe you can see the distortions here very plainly on the airplane. You can see it picking up on distortions very readily using this neural model. No modeling of blocking or anything else. Okay. So the biggest application scenario for this, of course, is in quality control of compression. We've got content, high quality in this case. We want to compress it, okay, typically using HEVC, H.264, whatever. We compare the raw and the original by perceptually optimizing the encode parameters. Now, this can be done on the fly, or you can do it like a lot of the streamers where you generate, 20 of them, and they're in the cloud, each one of those on a per-shot basis, perceptually optimized, Pareto optimal along a compression curve using VMAF. Okay? This technology won a Technology and Engineering Emmy Award a couple years ago because it's used everywhere. Okay. That's the past. I hope I've motivated that when you're using this, it's not just because somebody fiddled around and it worked. Handcrafted, that term we hear these days, especially in the machine learning. This is science. It's based on science. Okay? Okay, a couple of new use cases. One, high frame rate stuff. Okay, there are companies like YouTube, Amazon, very interested in live streaming of what? Sports and high action stuff too. Okay? How do we handle that? Okay? This research supported by the YouTube team, this fantastic student, Pavan, conducted this work. So, older frame rates, 30 frames per second. Today, 60 is pretty standard. But I tell you, you're interested in 90, maybe even 120. You doubt me? Well, we doubted 4K and we doubted 8K. I can go buy that on Amazon right now for $400, okay? It's coming because it can have advantages. Higher frame rates, of course, mean higher data volume. The internet is already stressed. We have to compress it more if you're going high frame rates, which means more potential distortions. We have to attend to video quality very carefully if we're increasing the frame rates, okay? Just to show you some examples of the kinds of distortions, I hope this shows up. I picked lower frame rates here, so in the hopes you could see it. So in this case, the high motion, which causes these distortions, it's called stutter, is from the camera moving. Okay, so here at a lower frame rate, look for how discontinuous the motion seems, and I'm hoping this thing doesn't like blur it out. It does a little bit, but especially when it picks up in speed, you see the stutter. I see it more here, believe it or not. There's some sort of temporal filtering going on. Here's at 60 frames per second. Much smoother perception. Now, if you're watching the football game and the running back is running across the field and the camera's not tracking it well, you will see this stutter. I notice it every time. I see it in basketball games all the time where the cameras aren't moving appropriately. It's a problem when there's high motion. Okay, so you need higher frame rates. Okay. So the kind of models I've just been describing, these neural processing models, Gaussian scale mixture models, will underlie how we approach this as well. I'm not even going to talk about the spatial side because this is a temporal problem, but we do combine same kind of spatial model as before, basically, but now a temporal model. Okay, notice entropy differences, same kind of thing. This should be familiar from the previous diagram. One other thing, we feed features to a very simple learning model, a shallow model called support vector regressor. It's not deep learning, it's just a shallow model, okay? So in this, we do bandpass decompositions of the signal, we compute entropies, but there is one other thing. We compute a signal called a pseudo-reference signal. Okay, we're going to study this, and we conduct a pseudo-reference signal, which I'll explain in a minute. The temporal bandpass filters that we use in this model is a Dobeshay wavelet. It's biorthogonal. We use it. It has nice properties. It's symmetric, unlike a lot of wavelets, and gives good results. Basic idea is we take our video, we bandpass filter with some number of temporal bandpass filters, which divide up the frequency space. So we have different pass bands. Okay. It's a model, again, of the area in the thalamus called the lateral geniculate nucleus. Well, temporal decorrelation occurs, reducing the data volume, making it more compressible. By the way, when I mention bandpass filtering, and you're saying, well, why is it more compressible and so on? Any bandpass filter can be written as a difference of two low-pass filters of the same shape, but different scales. It's a mathematical theorem. If we're differencing two low-pass versions of a signal, That's predictive coding. They're going to be similar. We get mostly zeros, things that are concentrated around the origin. Okay, so that's why bandpass filtering is always a decorrelating operation, especially on visual signals that have these special properties. Okay, this shows temporal bandpass versions of the same videos. Here at 24, looks chaotic whenever we have high motion. That changes the statistics. The highly reliable natural statistics of the video have been distorted. In this video, they're somewhat distorted. Maybe 60 isn't fast enough, but not as distorted. It's not nearly as chaotic. The statistics are much more regular, and we can compare these statistics and predict distortion, perceptual distortion, because we're doing a perceptual processing model. Okay, so here's a plot that shows how bandpass entropy is changed by frame rate. These are kind of small, so as the frame rates are high, these are high frame rates, the entropy is lower. As things get more chaotic because we have lower frame rates, the entropy rises. Okay, so this is 24 frames per second up here. So we get these big difference changes in entropy because of changes in frame rate over one content. And this is typical. These are typical. Now, for computing entropies, we need to separate this frame rate bit, which is very important, as I've just shown you, from the compression side. You know, the blocking and all that, scaling artifacts and all that. So we need to remove the bias of the frame rate when measuring the compression side, the spatial side, primarily spatial side. Okay? This is where that pseudo-reference signal comes in. Okay? So we assume a 120 frame per second reference. The pseudo-reference is just that reference signal downsampled to the same frame rate as the distorted video. So we have a reference, we have the distorted, and the pseudo-reference downsampled to the same frame rate as the distorted video. Okay? Why do we do that? Because in our model, well, we compute entropies of all three: reference, distorted, pseudo-reference, original and distorted videos, of course. This is a full reference model, okay? This shows what we call the generalized space-time quality features. We difference the entropies of the distorted and the pseudo-reference, and also we take a ratio of the reference and the pseudo-reference, okay? One of these measures compression distortion, and the other measures frame rate distortion independently. To see that, let's suppose there is no frame rate distortion because the reference and distorted have the same frame rate, then it collapses to just a different, that isolates compression distortion. If it's not compressed, but just has a different frame rate, then it isolates to a comparison between reference and pseudo-reference. Captures just frame rate distortion. Okay. So suppose you have an existing model, VMAF, multi-scale sim, something else out there. A deep model for video quality prediction, a VQA model. Okay, we have features which we feed to a simple learning model. We can also compute these new features in a parallel track. We're not subtracting information, we're adding this new information. Okay? These neurostatistical features are very powerful for measuring the kind of distortions I've been demonstrating. These are some famous algorithms, both sim and multi-scale sim, red models, speed, and of course VMAF. In each one of these blocks, you see an uptick in performance on a database that we constructed with YouTube of variable frame rate videos, a significant uptick in correlation with human quality judgments. Even a VMAF, we get about a 0.1. Anytime you get a 0.1 these days in video quality model upgrades, it's gigantic when we're usually going for 0.01. So this is very significant, and every model benefits hugely by the inclusion of the GTS features. Why is this important? Well, the whole goal of these perceptual models is to push compression as much as possible before the compression becomes noticeable. We can do it in space and time now. We can use this to push it for frame rate, variable frame rate cases. By pushing this, we use a lot fewer bits. We make everybody's experiences better. We make everybody's bandwidth better, especially as we start doubling frame rates and so on. And we impact the carbon footprint of the internet, which today is at least 5%, as I understand it, but is going to go up to 20%, I hear. And video is a big part of that. Well, this is one way, at least, of affecting that. Computation is another. Okay? These figures are small, but this will all be made available. This shows at different frame rates the correlations. Okay? What it shows is when you train all these models, sim, red, speed, VMAF, with and without these new features, you get very large increases in performance, especially at lower frame rates. I'll just read a couple here since I didn't know this was going to be so tiny. VMAF before, at 24 frames, 0.25 correlation. With these features, 0.75. VMAF does very well when we're at the high frame rate regime. Okay. Second use case, HDR. Another way in which video engineers are increasing data to make your experiences better. Instead of 8 bits, it's 10 bits, right? I'm simplifying. I'm going to keep things simple at that level right now. This work supported by Amazon Prime Video. Okay. So for many, long time we're used to, 24-bit video. HDR is wonderful. Okay, we have bigger, brighter televisions, 1,000 nits or more capable, darker darks, brighter whites, more vivid colors, etc. Okay? More data. Naively, immediately, it's 25% more data. Right? Well, we need to compress it more, that means. Which means, once again, we need these quality models to adapt to this, to measure this new phenomena of using deeper videos, deeper bit depth, okay? So if we compress more distortions, right? Okay, so as a preview, what we're going to do is something very similar to what we did. We're going to define features special for the HDR scenario, which we call HDR Max. They're very simple. Simple is good, right? The simplest, the most powerful concepts are often the simplest. So we can take any model existing, like VMAF or SIM or something else, even PSNR, compute HDR features, train it using a simple model, and we're going to get better results on video quality prediction of HDR. Whoops. Okay. HDR Max is super simple. We just scale the video to the range -1 to 1, which is often done anyway, and then we apply an expansive point nonlinearity of this form. This is fairly arbitrary. What it does, basically luminances or colors in the middle of the range get crushed. Okay, get crushed. While the ones at the darker darks, the more vibrant colors, the brighter whites, these get expanded. Why is this the approach that we're taking? Okay? The reason why is that most, even HDR videos, most of the content is in the mid-range. It's not that whiter. Most of it is, just usual sort of stuff. Maybe the TV is brighter, but the content is in the usual range. Video quality models like VMAF are saturated by that. Okay, the stuff in the darker regions and the brighter regions are largely ignored when measuring video quality compared to the rest. It's diluted by the rest. So this emphasizes those extreme regions. I can't show you HDR here. First of all, my laptop isn't, and that thing certainly isn't. But I can show you, nevertheless, what kind of thing occurs. So if this was HDR, this is a darker region, there are some distortions here. On HDR, they would be much more visible. That's the problem, is the distortions in those dark regions. Because the details are coming out, so are the distortions. Right? So in these areas, the distortions are very visible to a human. But most of the picture, when applying a VMAF or a SIM, is accounting for distortion elsewhere. This gets, even though it's very perceptually important, it gets drowned out. It's drowned out. Okay? By performing HDR Max, most of this is crushed into a narrower range. And now you can see, even on this projector, you can see the distortions coming out in the dark, dark region. And again, this isn't true HDR, so you're not seeing it enhanced like it should be. Okay, with that simple operation, I'm done with that already. Once again, we get dramatically increased correlations. If we have recently created an HDR database, this is freely available to anybody, supported by Amazon, videos with HDR and SDR, various ranges of compression, large-scale human study, once again, just like the YouTube study. We find that the correlations dramatically rise on this database. So for VMAF, for example, it rises from 0.6 something to 0.85. Once again, we could be saving billions of bits by using this. Hundreds of millions of dollars. The environment, by deploying this simple kind of model. Okay? These other databases are not HDR, and I only include them to show that adding the HDR Max does not sacrifice any performance on SDR data either. It's not like, oh, it just works for HDR. It actually improves things a little bit on SDR as well, sometimes substantially. Again, this is feeding the same sort of natural scene model. It's all based on the natural scene models that we've been talking about, the Gaussian scale mixture. So, just to finish up, video quality prediction, once thought of as impossible, because of science, understanding the statistics of real-world videos has become solvable. Okay? Not by modeling distortions in videos, but by measuring and modeling neural responses. Even though we can't actually go in and access them, we can still model them accurately. Now, you notice I didn't talk about deep learning here at all. Okay, well, isn't that all we talk about these days? Well, no, not really in this space. And you'll notice that today's dominant video quality predictors, for full reference, they're not deep models. Oh, yeah, there are deep models out there, but they don't really give you that much gain. A little bit for a huge amount of effort and computation and GPUs and so on. Whereas this, VMAF, you can just burn it into firmware. It's super fast. Why is deep learning not killing these models? They're science-based. Something to remember for the students in here doing deep learning on something involving where scientific measures. Can't forget the science, okay? Because that's truth. If you're modeling truth, that can trump data. Okay? Of course, the deep models can learn the truth, too. As far as the no reference problem, remember the picture I showed at the beginning? Many, many different distortions, impossible to model. Well, in that case, deep learning really does help. How does it help? It helps with the mapping from the same kind of statistical features to human perception. It's the mapping to how humans report those distortions that deep learning becomes very useful for. But that's a different talk. Just wanted to mention it. It requires very large data sets of very diverse, distorted pictures and videos. These are our sponsors. Thank you to all of them. You've made it possible. I especially want to thank Netflix and Ann Aaron, who were the first to put their faith in us in terms of funding our work. So questions. By the way, I'm a nut for visual illusions. And this is a great one, but it's also kind of a depressing one, because they're always walking forward, but they never get anywhere. It's called The Day It Rained in Lowry. I'm done.
So Thank you very much for this very, very interesting and exciting talk. We have 5 minutes for questions, so please. Come on. Don't be shy. Okay.
Thank you very much.
Just a second.
Whoa.
Oops.
Are we good now?
Yeah.
Awesome. Thank you very much.
My
I
pleasure.
believe I've got a handle on the special properties as they relate to a theater screen. Are there any special considerations, exceptions, or conditions that I need to know about as a video engineer as they apply to augmented reality or virtual reality screens?
Notice I didn't mention screens at all. Okay, so it has nothing to do with a cinematic screen, a television screen, or anything else. Okay, so the first part of the answer is for as long as the virtual or augmented reality is of real world content, meaning taken by a camera, photographic, okay, and generally for very realistic CGI too, okay, these models work beautifully. Okay? Now, as we enter the immersive space of XR, I would call it, there's a lot of other considerations, but these models can, and we've actually have used them and shown that they are wonderful and accurate for this. We've created a video quality model called FOV-QA that is intended for use in VR specifically. I got to tell you, I don't know what AR is yet, but I anticipate that, these scientific principles will not be lost in that space. There's other considerations, direction of attention, the gaze, foveation, right? Sheer data volume, the need for higher resolution for a display that's only an inch away from the eyeball, okay? Maybe more scales are needed, that sort of thing. So naturally these things will need to be modified and adapted, but the science won't go away.
Thank you.
Okay. More questions?
Amazing, a little bit over my head in parts. I'm not a VQ person, I'm more transmission, but the maths looks to me like it sort of had similarities to the point where Dirac introduced quantum mechanics.
Where what?
Where Dirac introduced quantum mechanics, it looks like it's coming to a tipping point. And I just wondered if you think there's a watershed moment coming, or there's so much that looks like waveform becoming operator mechanics in there.
Huh.
I just wonder if it's coming to a tipping point.
Okay, so I'm trying to figure out what's coming to a tipping point. So I will start out, but there are parallels with quantum mechanics. For example, the uncertainty principle. The uncertainty principle says you can't measure simultaneously position and velocity at the same time because of measurement. Well, the filters in Cortex are pretty much optimal uncertainty, meaning that they are optimally compact in both frequency and space and in time. As far as coming to a tipping point, golly, I think there's a tipping point we're reading about in the papers every day involving incredible capabilities of these machine learning systems. And maybe that's the direction you were talking about. Yeah, do I think that, well, we'll be talking about this tomorrow. I think end-to-end video communication systems, including compression, enhancement, quality control, transmission, communication, everything, is going to become, in some sense of the word, a big end-to-end learned system based on gigantic amounts of data which are available. Maybe it'll be modular, but it's going to be all heavily learned, okay? Which has been a big change for me, to try to teach image and video processing when all the old stuff I've been having to flush away and put in the machine learning stuff. Nevertheless, what are the machines going to be learning? They'll be learning these science models. They'll still be relevant and more efficient. Did that sort of answer the question? Otherwise, I can take it after.
Yeah, thank you, Professor, for this talk. It's very enlightening for me. What surprised me most is this Gaussian mixture model for images. So do I understand correctly that this is for natural images taken by cameras? Because as you know, there's also work going on screen content and like very artificial content. Yeah. Have you looked into that? Does this model also apply to that, or is this more for the...
Wonderful question. So the more photorealistic the artificial content is, the better the models apply. They actually apply pretty well until you get down to like 4-color or these you mentioned screen capture, which can have huge constant, if you have a blank screen, for example, it's not going to obey this model very well, okay? So it depends on the nature of the artificial content. But something like Avengers movie works great because the aim is photorealism, right? So I would say if the aim is photorealism and it's been achieved, then these models will work very well.
Thank you.
Yeah, I have a question because my background is from video coding, and a lot of these encoders make decisions still based on MSE, because this is what they can compute on a block basis, how they compute. Is there any way to also incorporate more of that model into a finer granularity on a block basis, where I guess still all modern video codecs operate on? So that would be really cool.
Absolutely, great question. I'm going to answer that in two ways. One is that a fellow named Homer Chen actually did this back in the 90s with SIM, okay? So making all the measurements instead of SAD using SIM. SIM is so efficient, you can do that, okay? So very possible to do it. Now, who knows who's doing it? After all, we don't dictate the encoder, right? Just the decoder. So I want to talk about mean squared error a little bit and the compression community, okay? Compression community has remained resistant. MPEG, I'm talking to you, Gary Sullivan, who I love to rib. Okay, he's my favorite target when I give a talk because he doesn't mind. He's a great guy. Okay, when you're showing results with respect to PSNR, this pointwise measurement, well, you're tuned to what you optimized over. Pointwise measurement, as you just pointed out. If you're optimizing over the mean squared error, well, of course your mean squared error is going to be, but that doesn't matter at all for how it looks, demonstrably, through incredibly extensive experimentation, proof, and basic science. Mean squared error isn't any good. Okay? So two halves to that question. So yes, they should do that more, and it's not a good measure of compressed video quality.
My point was half answered, I have to admit. My point was, for example, VMAF is very great for this chunk-based encoding approach. So you have a chunk, you encode it, you measure VMAF on it, and that works perfectly in that chunk-based environment. However, if you don't have the possibility to have multiple encodes and optimize it, you cannot use VMAF, for example, to do block-based decisions in an encoder. So this is what you only can do.
You could, actually. Like I said, it's already been done with SIM a long time ago, okay? And, the chunk-based is a choice made by the streamers. They could optimize on a per-frame basis, okay, if they wanted. It's just a choice. But doing it on a chunk base makes sense because it's really per-shot basis. You've got this homogeneous content over that time period.
That's true, but then you go into live encoding. You can't do.
It depends. You can. Why not? Computational limitation. Going back to Tom Wong. Tom Wong used to say, it was a joke of his. He would say, most of the advances in computer vision, image processing, video, are advances of the computer. Okay? It was a joke he made, picking at the fields. But, really, there's no reason why you can't implement real time on a per frame basis. Right now, today, British Telecom streams like 32 live channels on a per frame basis using SIM as the encode optimizer. Okay. So it's done. With VMAF, why not?
Well, I haven't seen it yet, so that's why it has
Not
to be a
seeing it is
reason.
the same as not done.
Okay.
So the streamers, for good reasons, are doing it on a per shot basis. No reason to do it. For live streaming, other decisions might be made.
Okay, thank you.
No limitations to computation or representation.
Okay. You have a question?
Just the last one.
Okay, short. Okay.
Thanks, Professor Bovik. One question I have is about HDR Max and the results shown. Were those results retrained on the data sets where these numbers were demonstrated?
Absolutely yes, for fair comparison. Every model was retrained with their features and with HDR Max.
Got it. And what is
With and without HDR Max, mind
yeah.
you.
What is the intuition on HDR Max helping on the ETRI one, so the middle column, and the one on the right, the live stream
Oh,
one?
you mean we're at 3 databases?
Yeah.
So the one on the left was a true HDR database, huge jumps in performance.
Yep.
Then we had an SDR 10-bit database, which is our ETRI database, and then the live stream, which is standard SDR 8-bit kind of database. Those were just to show that including HDR didn't lose performance, but nicely it shows it gains performance. Because actually our model doesn't require modeling HDR. It's really just emphasizing the dark and bright regions, which is really good in HDR, but it's also good in SDR to do that. So having that parallel path, a little extra computation. If it's HDR, huge boosts in performance. If it's SDR, no harm, some gain.
Okay, got it. Yeah, thank you.
Thank you very much for this great talk. We really don't, it should be really fast because
So you emphasized bandpass filtering a lot today, and also you mentioned wavelets. They've been around for a long time, but somehow they never really took off in the video encoding world, except some specialized applications. So it's been mostly in the DCT direction. So why do you think that's
Well, first let me point out that DCT mathematically, according to wavelet theory, is a bandpass operation when performed on a block basis. These models apply to DCTs performed on a block basis. You look at DCT coefficients, Gaussian scale mixture model applies very nicely, in fact. In fact, it explains why the DCT works so well, okay, why it's near optimal. So why did wavelets not? Well, I remember the wavelet days. I was involved in it, wrote a lot of papers on wavelets. We were anticipating they would kill video compression back then. And we remember something called JPEG 2000. I don't want to pick on, I already picked on Gary because he doesn't mind. I'm not going to pick on the JPEG 2000 guys too much. But one of the main advantages of using wavelets were you don't need blocks. What did they do with the first thing in JPEG 2000? They blocked it up. Okay, you have these different, I forget the names, they're very hard to remember, but they had 2 different kinds of blocks, and it gave better performance than JPEG, good old JPEG, which is still here, survived that onslaught, okay? Because, in the range up to about, 20 to 1, they're comparable. Beyond that, JPEG 2000 was better, but still wasn't good quality. So,
Thank you.
yeah, but wavelets are coming back. Tomorrow we'll talk about deep models. And after all, what are deep models doing in the early layers? Massive wavelet decompositions. So they're going to come back, but in the machine learning field.
Okay, thank you very much for this exciting and very interesting talk. Let's thank the speaker.